This video is Lab 1 for Physics 2211, Section N on constant velocity. In this lab, I'll observe an object, in this case a foam basketball, move in the x direction with constant velocity, meaning there is no net force acting upon the object. This result can be explained by Newton's second law, which states that the net force equals mass times acceleration, or the net force equals mass times the change in velocity over the change in time. So if the object is in constant velocity, the acceleration or change in velocity would be zero, resulting in a net force of zero. The momentum principle can also explain this result because it states that the change in momentum equals the net force times the change in time, and with an object in constant velocity, the change in momentum is zero, which would evaluate the net force to be zero as well. The purpose of this lab is to use the observation of an object in constant velocity to then predict the future position of this object, assuming it maintains constant velocity, with the formula for average velocity and the position update formula. Now, I have recorded a video of a foam basketball rolling across the ground, which is being shown as I speak. Next, to analyze this video and record observed data of the ball's position over time, I upload the video to Tracker. In Tracker, I have set the frames from frame 42 to 63 to capture the ball while it is in constant velocity and before it disappears from the video. Next, I set the origin of the axis to the ball's center at frame 42, which means as the video runs, the ball will move along the positive x direction. Then, I measure the center of the ball's position at each frame from frame 42 to 63 to record the observed time and position in Tracker. With this data, I upload it to a spreadsheet to analyze it next to the predicted data, which I'll create using a computational model in GlowScript. In GlowScript, I've created a computational model to predict the foam basketball's position, assuming it maintains constant velocity. In the code, I must make changes to values in order for it to apply to the foam basketball used in my video. First, I will change the radius of the ball to 0.05 meters and the mass of the ball to 0.25 kilograms. The initial position will remain at 000 meters, but the initial velocity must be changed to the average velocity of the foam basketball in the video, which can be calculated using the change in position over the change in time, which from the observed data is approximately 0.42 meters over 0.7 seconds, which equals 0.6 meters per second. However, the initial velocity in the code must be related to the delta t we input into the code, which is 0.033 seconds. So the initial velocity must be 0.0198 meters per 0.033 seconds. Within the loop, I will find the predicted position while time is less than a second, and I will set the net force to be 000 and the position update equation in the loop to add 0.0198 meters for every change in 0.033 seconds. I will then run the code to collect the predicted positions of the foam ball, which I will enter into the spreadsheet with the observed data to compare the observed and predicted positions. In this spreadsheet, we have compiled the observed position, predicted position, and time into tables as well as a single graph. In the graph, the blue dots represent the observed position values from the tracker, and the red line represents the predicted position as an equation where the predicted position would equal the initial position, which is 0, plus the velocity, 0.6 meters per second, times the change in time. The predicted position and observed positions have about the same values, where the observed positions follow the trend of the predicted positions. However, there appears to be a slight discrepancy from about 0.3 seconds to 0.5 seconds on the graph, where the observed positions are greater than the predicted positions. After performing the lab, I need to analyze the data comparisons between observed and predicted position, as well as clarify some questions which can change the results of the lab. First, what if I had oriented the ball along the y-axis? For example, instead of rolling on the ground, I dropped it. At first, it may appear to be the same as rolling it, but by dropping the ball no longer has a net force of 0 because gravity will push down the ball. Next, how many forces are counteracting on the ball, which results in a net force of 0? There's a force of gravity acting on the ball in the negative y direction, and since there's a net force of 0, there has to be a force by the ground acting on the ball in the positive y direction, which is the normal force. For the x direction, the ball is moving in constant velocity, so no force is pushing it. But since the ball is rolling on the ground, there's a force of friction in the negative x direction, but in order to get a net force of 0, we would have to assume friction is negligible. This means there's one counteracting force, one push and one pull in the y direction, which is gravity and the normal force. Finally, we must analyze the comparison between the observed and predicted positions. Overall, it appeared to follow the same trend, but there was a small discrepancy between the times 0.3 and 0.5 seconds, where the observed position was greater. The possible reason for this result is that the predicted model constant velocity is set, but in the observed model, it is assumed. In reality, the ball in the observed model has an initial push, which means there was acceleration, which would cause the observed model to be greater because the velocity is increasing. Additionally, friction is pushing the ball in the negative x direction and causing the ball to slow down and have a negative acceleration. So if the observed and predicted models continued after 0.7 seconds, the observed position will begin to fall below the predicted position. In conclusion, the lab served its purpose by allowing me to predict position of an object based on Newton's second law, the momentum principle, and assumptions of constant velocity. And although in reality there was friction and initial force to move the ball, the observation had a set period of time where constant velocity could be assumed to create a model to predict the position if this constant velocity was maintained. Thank you.